Picture this. June 4th, 1996. The brand new Ariane 5 rocket is on its maiden voyage. 37 seconds after liftoff, it explodes. A self-destruct sequence was triggered. But why? Not a mechanical problem. It was a single line of code, a software bug. A simple data conversion error that turned hundreds of millions of dollars and a decade of work into a fireball in the sky. It's probably the most dramatic example of just how high the stakes are when we engineer software.
So how do we stop things like that from happening? How do we actually build the incredibly complex software that runs our entire world, from our banks to our phones to our spacecraft? Well, it's not just about writing code. It's about engineering. So today, let's pull back the curtain on this unseen world and find out how software is really put together.
All right, here's our game plan. We're going to walk through the whole journey. First, we'll look at the fundamental challenge and why software fails. Then, we'll see how an idea becomes a blueprint. We'll talk about architecting the solution, hunting for those hidden flaws, and then what happens during a system's very long life. And finally, we'll take a peek at what's coming next. To really get why software engineering even exists, you first have to understand the problem it's trying to solve. Why is building good software so ridiculously hard? It really boils down to a few key ideas. First off, we got to get our language straight. A developer might make a mistake in the code, a little bug. We call that a fault. That's the internal problem. But it only becomes a failure when you, the user, actually see it happen, when the app crashes or the wrong number shows up. And here's the key. A fault can just sit there in the code, totally dormant for months, even years, until the one specific set of circumstances happens that triggers the failure.
And this really gets at the huge difference between just, writing a program and actually engineering a system. There was a study that really shows this perfectly. They had these two kinds of teams. The unstructured creative teams, they always built these amazing, elaborate Taj Mahals out of construction paper, but they were never ever finished on time. And the structured, disciplined teams, they built a simple, functional Days Inn hotel. And when the clock ran out, it was finished and ready to go. See, engineering isn't just about being creative. It's the discipline of building things that actually work on time and reliably.
And the stakes can be terrifyingly high. Take the Therac 25. It was a radiation therapy machine from the 80s. Hidden software faults, those dormant bugs we talked about, led to patients receiving massive overdoses of radiation. People were severely injured. Some died. This isn't just about an app being annoying. This is literally life-or-death engineering. So how do we apply that engineering discipline to prevent these disasters? Well, it all starts with a blueprint. You wouldn't just start nailing boards together to build a house, right? And you can't build good software without a rock-solid plan. In our world, that plan is built from requirements. The process for getting that plan is really methodical. First, you have to elicit the requirements, which is a fancy way of saying you have to figure out what the customer actually wants, which can be surprisingly hard. Then you model it, maybe build a little prototype so they can see it. After that, you specify it all, write it down in a clear document. And finally, and this is so important, you validate it. You go back to the customer and say, hey, look at this. Is this really what you had in mind? Now, that whole process sounds pretty straightforward. But what's the difference between a vague wish and a requirement that you can actually build something from? What makes a requirement a good requirement? Well, a good one has a few non-negotiable traits. Of course, it's got to be correct and unambiguous. But the one that really matters, it has to be testable. A requirement like the system should be fast, that's totally useless. How do you test fast? You can't. But a requirement that says the system must respond to 95% of user clicks in under half a second, aha! Now that is something you can build and something you can test to prove you built it right. Okay, so now we have our blueprint. We know what we need to build. The next giant question is how? This is the architecture phase. This is where we design the skeleton, the whole underlying structure of the system. And just like buildings have architectural styles, Gothic, mid-century modern, whatever, software does too. An architectural style is a big established pattern. It's like a template for how all the different pieces of the system are going to communicate, how they're going to stay in sync, and how they're going to share data. So, for example, you've got the classic client-server style. Think of a bank.
There's a big central server that has all the account information, and your phone app, the client, has to ask it for permission to do anything. The server is the boss. But then you have a style like peer-to-peer. Remember the original Napster? There was no central boss. Every computer on the network talked directly to every other computer to share music. That single decision, which style you pick, completely defines how the rest of the project will go. All right, you've got your requirements, you've got your architecture. You build the thing. Job done, right? Let's go home. Not even close. Now comes what I like to call the gauntlet. This is the aggressive, organized hunt for all the mistakes you've definitely made along the way. And to do this right, you have to kind of flip your brain upside down. The point of testing is not to prove that the software works. The point of testing is to find where it's broken. You are actively trying to prove the existence of a fault. A test is only considered a success if it finds a bug. It's a total mindset shift. You're not a builder anymore, you're a hunter. And faults are your prey. So where are you hunting for these things? Where do they come from? Most people think it's all in the coding, typos and logic errors. But that's not the whole story. The data shows that a whopping 60% of all faults, they actually start in the requirements and design phases, long before anyone has written a single line of code, which shows you just how crucial getting those early stages right really is. So this hunt happens in stages. You start small. Unit testing is where you test every tiny little piece by itself in isolation. Then comes integration testing, where you start snapping those pieces together and making sure they play nice with each other. And finally, there's system testing. That's when you test the whole complete product against those original requirements you wrote down way back at the start. The software is delivered. The customer is happy. The credits roll. The end. Right? Nope. We're now entering what is almost always the longest and most expensive part of any software's life. Everything that happens after it's delivered. We call this phase maintenance, but that word is a little misleading. It's not just about fixing things that break. Really, it's about any change you make to the software once it's out in the wild. Whether you're correcting a fault, trying to make it run faster, or adapting it so it works on the new version of Windows. We can actually break maintenance down into 3 main types. You've got corrective maintenance. That's what you think of as standard bug fixing. Then there's adaptive maintenance, like when you have to update the app to work with a new security protocol. And finally, there's perfective maintenance. This is when you improve the system even though nothing is technically broken. You're making it faster or easier to use, or just cleaning up the code. So why do we go through all this incredible, painstaking effort? The requirements, the architecture, the testing. Why? It all comes down to this one absolutely mind-blowing number. Finding and fixing a problem in the requirements phase might cost, say, $1. Finding and fixing that exact same problem after the software has been delivered to customers can cost up to 200 times more. The entire game is about finding problems as early as possible. Okay, so this whole disciplined process, this is what has allowed us to build the modern world. But the world keeps changing. So what's next? What new challenges are waiting for us just over the horizon? Well, the future seems to be all about what we call ultra-large-scale systems. Think about smart cities, or global logistics networks, or self-managing power grids. We're talking about systems with maybe thousands of sensors, constantly making decisions, and needing to adapt to things their creators never even thought of. For systems that complex, the whole idea of being perfectly correct, like in a math problem, well, it might just be impossible. And that leaves us with a really fascinating and maybe a little scary question to think about. As our software systems become more and more like living organisms, self-managing, evolving, and almost impossibly complex, does our whole goal as engineers need to change? Are we going to have to shift from trying to build perfectly correct software to being able to build software that is just sufficiently correct? That is the big question for the next generation of software engineers.